Hi, welcome to the Euclidean Geometry 101 course. We will show an important proposition about perpendiculars and oblique lines and a few corollaries. We will end this chapter with the definition of distance from a point to a line. But before attacking that proposition, a little something about what an oblique line exactly is. An oblique line is also called a slant line, and it is a line that is not perpendicular to the other line. To stay in the same vein as the definition for perpendicularity, an oblique line forms unequal angles with the line she is oblique with, and that in contrast with a perpendicular on that line. When one drops a perpendicular and several oblique lines from a point outside a straight line onto that line, one can observe 1. That the perpendicular is shorter than any oblique line, 2. That two oblique lines have the same length when the feet of the oblique lines are equidistant from the foot of the perpendicular, and 3. That the oblique line whose foot lies the farthest away from the foot of the perpendicular is the longest oblique line. We will prove every part of the proposition separately. For the first part, we observe in the figure a perpendicular OD and an oblique line OB both dropped on the straight line AC. We need to prove that OD is always shorter than OB. Let's extend OD to O' with O'D equal to OD. Now draw the segment O'B. Observe the two triangles that have been formed. Triangle ODB and O'Db. They are congruent, and this can be proven applying the SAS case of congruency. First of all, the angles formed between OO' and BD are right angles. Secondly, by construction we have that O'D is equal to OD. And thirdly, the side BD is a common side. So, there are two equal sides and an equal included angle. And this means that all other parts of the triangles are also equal. Specifically, side OB is equal to side O'B. In triangle OBO', we know that the side OO' is smaller than the sum of the two other sides. So OO' is smaller than OB plus O'B. And OO' is the sum of OD and O'D, so we have the inequality OD plus O'D is smaller than OB plus O'B. By construction, O'D is equal to OD, so this becomes 2 times OD is smaller than OB plus O'B. And we have proven that OB is equal to O'B out of the congruency of the two triangles ODB and O'Db. So 2OD is smaller than 2OB. Eliminating the 2, we arrive at the conclusion that OD is smaller than OB. And that's what needed to be proven. For the second part of the proposition, we start with two oblique lines, OB and OC, and of course the perpendicular OD. And we have that the feet of the two oblique lines have the same distance from D. So, the line segment DB equals DC. We now need to prove that the oblique lines OB and OC have the same length. OD is a perpendicular, so the angles in D are right angles. Thus, the triangles ODB and ODC are congruent triangles according to the SAS case, because we have equal included angles between equal sides. Therefore, OB equals OC as other elements of those triangles. For the last part of this proposition, we consider the two oblique lines OA and OC, where the foot A is farther away from D than the foot C. Ergo, AD is greater than CD. Now let's take another point B on AC as a foot and have the point B as far from D as the point C from D. So DB equals DC. Now draw OB. According to the previous case, OB equals OC. Now by construction, the point B lies between A and D, and so OB lies between OA and OD. In other words, in the angle OAD. Let us now extend OD to O' with O'D equal to OD. And draw the segment O'B, just like we did in the first part. We saw that OB is lying between OA and OD, and as OO' is the extension of OD, OB is also lying between OA and OO'. Remember the first corollary we saw for proposition 14. That corollary stated that the sum of the distances from a point inside the triangle to the endpoints of a side is smaller than the sum of the two other sides. Apply this now to the triangle OAO', with B being the point inside of the triangle. This gives us the inequality BO plus BO' is smaller than AO plus AO'. Now consider the line OO' on which OB, O'B, OA and O'A are all oblique lines. BD and AD are perpendiculars on that line OO'. We know that O and O' are equidistant from D. So the oblique line OB is equal in length to O'B. Likewise, the oblique line OA is equal in length to O'A. Substitute this new information into the inequality and we get 2OB is smaller than 2OA. Therefore, OB is also smaller than OA, or OA is greater than OB. And because OB is equal to OC, we have finally that OA is greater than OC. The converse of the proposition is also true. 1. The shortest distance from a point outside of a straight line to that straight line is the perpendicular from that point on the straight line. 2. The feet of two equal oblique lines is equidistant from the foot of the perpendicular. 3. When two oblique lines are not equal, then the distances of the feet of those oblique lines to the foot of the perpendicular is not equal, and the longest oblique line has a foot that is the farthest away from the foot of the perpendicular. To prove the first statement, let's consider OD to be the shortest distance of O to AC. If OD is not a perpendicular on AC, let's then call OD' the perpendicular from O to AC. In that case, OD' is shorter than OD. And that conflicts with the given. To prove the second statement, we consider OB and OC two oblique lines with the same length. If DB were different from DC, then the direct proposition states that OB is different from OC. Therefore, we have again a conflict with the given. And for the third statement, we consider two oblique lines OA and OC with OA greater than OC. The feet we call A and C. If the distance of the feet to the foot of the perpendicular were the same, then the direct proposition tells us that the oblique lines are equal, which conflicts with the assumed. On the other hand, if the distance from A to the perpendicular was smaller than the distance of C to the perpendicular, then we know out of the direct proposition that the oblique line ending in A must be smaller than the oblique line ending in C, again contrary to the assumed. So the only possibility that remains is that AD is greater than DC. We can infer a few corollaries out of this proposition. First of all, it is clear that from a point outside of a straight line, one cannot draw three equal oblique lines to that straight line. The reason of this being that out of the point on BC we can only measure 2 times the same length, namely to the left in one direction and in the opposite direction to the right. Secondly, in a right-angled triangle, each rectangular side is smaller than the oblique side. Consider the right-angled triangle DOC. OD is the perpendicular out of O on DC, and OC is an oblique line. So OD is shorter than OC. But because of symmetry, CD is the perpendicular out of C on OD, and OC is again the oblique line, now out of C on OD. So DC is also shorter than OC. In conclusion, OC is longer than OD and DC, or in other words, the rectangular sides are always smaller than the hypotenuse. The last corollary states that in a right-angled triangle, the angles adjacent to the hypotenuse are always acute. We know that the oblique side of the triangle is longer than the rectangular sides, and we know from before that opposite a larger side we have a larger angle. So the angle opposite the largest side, the hypotenuse here, is larger than the angles opposite the 2 other sides. But the angle opposite the hypotenuse is a right angle, and therefore the other 2 angles are smaller than a right angle, or acute angles. We can now also finally define the distance of a point to a straight line. It is the length of the perpendicular from this point to the straight line. That's it for this lesson. If you like this series, consider subscribing to my channel.